All right, these sorts of questions are some of my favorites, I gotta say. When you get this really interesting, composition of functions going on, and we have to find some areas, and it looks horrendous, but the question is going to kind of guide us through so that in the end we can find the shaded area. Right, so we're given a figure, and we're told that actually it's going to start at x is equal to 1. Well, we're just looking, sorry, yeah, we're just looking at x is greater or equal to 1. If we put an x equals 1, then we're going to get 0 out of it because ln 1 is 0. But we're also then interested in where the position of a. So it first crosses the x-axis at point A, find the x-coordinate of A. So to do this, we can set x sine ln x equal to 0. That's my value of y. It's when y is equal to 0. And then because x is greater or equal to 1, I can just divide through by that. And so I've got sine ln x is equal to 0. Now, of course, one solution of this would be that ln x is 0, because when you solve sine, basically I'm solving sine x equals 0 essentially. That's going to look like that. So my first solution is 0, but that will just give my x is equal to 1, which I already have. So my second solution is going to be here. And we're, of course, working in radians because we're doing, integration sort of question. So it's going to be pi. I'm going to get that ln x is equal to pi. And that means that x is going to be e to the pi. And that's going to be my x-coordinate of A. Sorted. Right, now we're asked to differentiate x sine ln x and x cos ln x, and hence find these integrals here. Right, focus on the differentiating to start with. Okay, for this we can use first of all, the product rule. So it's going to differentiate x, which gives me 1, and times by this, sine ln x, and then add x times the derivative of sine ln x, for which I need to use the chain rule. I could write all this down formally, but at this point, the hope is that you're really confident with the product rule and the chain rule, and we can do this as quickly as possible. So when I differentiate sine, I'm going to get cos. It's going to be cos ln x, and I'm going to times by the derivative of the inside, which is going to be 1 over x. And they're going to cancel. That's pretty neat. I'm going to get sine ln x plus cos ln x. Now I'm going to differentiate x cos ln x. It's going to work out in a similar way. First of all, differentiate the x and times by the cos ln x. And then I'm going to add x and differentiate cos ln x. Okay, this time when I differentiate cos, I'm going to get minus sine. So it's going to be minus x times sine ln x. And then again, I'm going to times by the derivative of ln x, which is 1 over x. And they cancel. So I get a very similar result, but it's cos ln x minus sine ln x. Now we're asked to find the integral of sine ln x. But there's something going on here in that we've got the derivative of two things, and we've got sine and cos of ln x, and same again, but here we're minusing. So look what happens if I subtract them. If I do d by dx of x sine ln x minus d by dx of x cos ln x, and I can actually put that in a big bracket like this, then I'm in fact going to get 2 sine ln x. Okay, sort of like a simultaneous equations kind of problem. And therefore, well, I can divide through by 2. I don't know. I'm just going to do it here. A half of that is going to equal that. And therefore, the integral of sine ln x, because if the derivative of this top bit is sine ln x, and the integral of sine ln x is simply that top bit without the d by dx. So it's going to be a half. I can even factorize out the x. A half x sine ln x minus cos ln x. Of course, don't forget the plus c. That's pretty neat. And then to get the other one, I'm going to need to add them together. That's going to be 2 cos ln x. So again, I can divide through by 2, and therefore the integral of cos ln x. Of course, I can bring that half inside. Like I didn't really talk about that, but if you differentiate something and then times it by a half, it's the same as just timesing both by half and then differentiating. I can factorize the x out. Plus another constant. Maybe I call it C1 and C2 just to distinguish them. Yeah, it's pretty awesome, isn't it? Okay, on to the main event, which is to work out this integral, and then in a minute we're going to find that that enclosed area. Now, there's actually 5 methods given in the mark scheme for doing this, and I'm just going to briefly talk about four of them, and I'll show you the way that I'd like the most. Okay, one way of doing this question is to actually do a substitution. U is equal to ln x, and that will work out quite nicely. You'll do a similar sort of process to what you do in the other methods, but it's kind of simplified a little bit because of the substitution. Now, I don't think that's particularly intuitive, especially given all the stuff we've done before. Like when you're doing this question, you end up thinking, surely I've got to use some of this stuff up here, but it does work. Method 2 is to recognize that we have actually differentiated this earlier on. And so if you times it by 1, you do kind of what you do when you integrate ln x. We're going to actually call this v dash. So v will be x, and then this will be u, and we'll find u dash. I like it, but I don't think it's really intuitive because how do you know it's going to work out? You learn it for ln. I know there's a ln in it. Um, yeah, it just didn't jump at me and think, yeah, that's an obvious thing to do. Now the way I did it was not it's not the best method, I don't think. So I'm actually not going to show you this one. It's just unnecessarily complicated. But for me it was the most intuitive when I did it, and it was actually to call this u and this v dash because that's typically what you do when you integrate x sine x or x times e to the x. You always let u be the x because it seems to make things simpler. Um, in this case, it does, but not before it introduces lots of fractions and things. It's just very easy to make mistakes. And if I did actually make a video going through it, but it just felt clunky. So look it up or try it that way if you want. You know, you will get the right answer. In fact, the best way that I saw in the solutions to do this is instead of just swap them around. So actually, this is going to be u and this is going to be v dash. Now, you might say that's also not that intuitive because it seems to be making things complicated, but you know when you differentiate this bit here, we're going to be timesing by the derivative of ln x. So it's going to kind of work itself out. It is also one of the easiest methods to understand, I think. So I'm going to go through it using this method here. So I'm going to get u dash is equal to, using the chain rule, cos ln x times by 1 over x. And then v is going to be more complicated. It's going to be a half x squared. And then my integral is going to be uv minus the integral of u dash v, which is going to give me a half x squared. By the way, I'm going to call this s. You'll see why later on. You might not think of it at the time, but just making reference to it now. It's going to be half x squared times sine ln x minus u dash times v. So it's going to be cos ln x times 1 over x times a half x squared. And the 1 over x and the x there are going to cancel. I can bring the half out, and I can actually, I'm just going to bring the x to the front. And now I need to work out this integral here, which I'm going to call c. So for c, I'm going to do integration by parts again. And now I'm going to let, similarly, this is going to be u, and this is going to be v dash. Let's be consistent and stick with that. If we swapped it around, we'd actually get back to the start. It wouldn't help. So u dash is now going to be minus sine ln x times 1 over x, and v is going to be a half x squared. So c is equal to uv, so a half x squared times cos ln x minus u dash. Now there's a double negative here, so it's going to be plus. And then I'll put the half x squared first, times it by sine ln x, and then 1 over x. This cancels with that part. I can bring the half out. And in fact, I've got back to s, which you might think is not good, but it actually is. And if you've done questions like this in, it doesn't come up in A-level maths. But if you'd seen it in the Advanced Extension Award before, and you should be practicing these papers, then you'd know what to do from here on. But if you haven't seen it, then I'm here to show you. So we've now got s. So therefore, back to s here, I've got a half x squared sine ln x minus a half, and I'm just going to replace c by this thing here. It's going to be plus a half s. It's really useful sometimes to just call integrals by letters, because otherwise it's just going to, it's going to be unnecessarily complicated. Right, this is going to become minus a quarter x squared cos ln x, and then I'm going to minus a quarter s. And now I can add that on to both sides. So actually, I'm just going to have s by itself. It's really nice when you just get s on the left, s, and plus some other terms on the right, but it's times by a fraction of some sorts. You can combine it together. It's going to be 5 over 4s. And I'm going to factorize out a quarter x squared. That's going to give me 2 sine ln x minus cos ln x. And therefore s is going to be, I'm going to times by 4 and divide by 5, 1/5 x squared. This is a nice factorized version of it. Okay, don't if yours is messier than this, then don't be surprised, because I've kind of I've gone through and I've tried to optimize my solution. You know, it's very easy after doing all this to actually forget about the constant, but you need to add that at the end. I could have, like, technically, I could have added it at various different points, but if I'd added it, say here, when I times by the fraction, it would have affected the constant. So just, if it helps, I guess, add it in earlier, but you know, just make sure you don't forget it. I don't know, it'd be harsh if you got penalized for it here, but you should always remember to include it. So that is our value of s. I probably should just write that it is what the original thing is. It's this integral here. Yeah, that's my preferred method. You know, still a fair few lines, but nowhere near as many as when I swap these two around. Not as many fractions, and I think it's pretty okay to understand. Hope you're happy with that anyway. Okay, that leaves us finally to work out the area of the shaded region bounded by the curve and the x-axis between the points 1, 0, and A. That is this shaded region here. So we're going to need to integrate the function x sine ln x between the limits 1 and e to the pi. We've already done the integrals, so it's just this definite integration, 1/5 x squared, 2 sine ln x minus cos ln x. And I can ignore the constant. So when I substitute an e to the pi and square it, I'm actually going to get e to the 2 pi by combining the indices. Then it's going to be 2 sine ln e to the pi minus cos ln, sorry, minus cos ln e to the pi. Then I'm going to minus the same thing when I substitute 1 in. 1 squared is just 1. So 1/5 e to the 2 pi 2 sine. Now ln of e to the pi is actually just going to be pi. So it's going to be 2 sine pi minus cos pi. Then minus 1/5 2 sine 0 minus cos of 0. Now, actually, sine 0 is just 0, and sine pi is also just 0. Meanwhile, cos 0 is 1, and cos pi is minus 1. So I'm going to get 1/5 e to the 2 pi, the double negative, and then I'm also going to get plus 1/5 because there's another double negative here. I'm minusing a minus. And I can factorize out the 1/5, so it's going to be 1/5 e to the 2 pi plus 1. That's our area. Okay, well done with this question. Really good question, isn't it?